Now this is moving on from the power rule that we discussed before. This is Fermat's little theorem. We note that from the power rule that 1 to the 4 equals 2 to the 4 equals 3 to the 4 equals 4 to the 4 equals 1 modulo 5. So a is an integer that is not a multiple of 5. Now we suppose a is an integer that is not a multiple of 5. So we know that a equals 1 modulo 5 and a equals 2 modulo 5. A equals 3 modulo 5 or a equals 4 modulo 5. Therefore, by the power rule, we have a to the 4 equals 1 modulo 5. Now, this is a special case of Fermat's little theorem, which is defined here, which states that we let P be a prime and let a be an integer that is not a multiple of p, then a to the p minus 1 equals 1 modulo p. Now here's an example. Find the least residual of 4 to the power of 20 modulo 7. We know that 7 is prime, so Fermat's little theorem holds. So 4 to the 6 equals 1 mod 7. Therefore 4 to the 12 equals 4 to the 6 squared equals 1 squared equals 1 mod 7. And 4 to the 18 equals 4 to the 6 cubed equals 1 cube equals 1 mod 7, and so on and so on. Now we can simplify by writing 20 is a multiple of 6 plus a remainder. Now, since 20 equals 3 multiplied by 6 plus 2, we obtain by simple power rules that 4 raised to the power of 3 multiplied by 6 plus 2 equals 4 to the 3 multiplied by 6 multiplied by 4 to the 2, which equals 4 to the 6 cubed multiplied by 4 squared. So 4 to the 20 equals 4 to the 6 cubed multiplied by 4 squared equals 1 cubed multiplied by 4 squared equals 16 equals 2 modulo 7. 2 modulo 7. So the least residue is 2 from using Fermat's little theorem. Now I should probably have covered these before on like power rules and arithmetic rules, but the multiplicative inverse modulo n, this is basically the definition of what it is. A multiplicative inverse of a modulo n is an integer v such that av equals 1 mod n. Example, 5 is a multiplicative inverse of 2 modulo 9 because 2 multiplied by 5 equals 1 mod 9. Now here's a definition of linear congruence. A linear congruence is a congruence of the form ax equals b mod n, where a and b are known and x is unknown. Here's an example. Solving a linear congruence when a and n are not coprime, we solve 12x equals 16 mod 20. Now the solution. The highest common factor of 12 and 20 is 4. Since 16 is divisible by 4, the linear congruence is solvable. So we established that this is solvable. So now we divide each integer 12, 16 and 20 by 4. So we get this here. Now since the numbers are small, we try values 1, 2, 3 and so on. So 3 multiplied by 1 equals 3 mod 5. 3 multiplied by 3 equals 9 equals 4 mod 5. So solutions are given by x equals 3 mod 5. And yeah, that's Fermat's little theorem. At least that's what we began with. Please do like and subscribe. I've got plenty more to come.